So you've got about 10 to 12 minutes to work on this one. This is a calculator question, so do your best, and I will check back in a few minutes. So we're given a chart of values, and we are given some information about f of x, where that f of 3 is equal to 2, and that f prime of x is x cosine of e to the x. Right? So first thing we're going to try and do is figure out what f double prime of the sine of 2 is. And since this is a calculator problem, we should just be able to go in and use calculator to evaluate what the derivative of that function is. Okay? So my graphing calculator just crashed on me. All right, so using the graphing calculator, sorry about that, we should end up with math and then option 8 for the derivative. And so we're looking for the derivative with respect to x of our f prime, which is x cosine of e to the x. So x cosine e to the x. And we're looking to evaluate that at the x value that is sine of 2. Everybody good with that? Looks like it comes out to be negative 2.173. Is that what you all got?
Yeah.
Perfect. So the derivative with respect to x of x cosine e to the x evaluated at the sine of 2 is negative 2.173, I think, right? Yeah. Any questions on that? All right, what about part B? Where now we're looking at a new function, h of x, where h is g of f of 2x. And we're looking for h prime of 1.5. So h prime should be the derivative of g of f of 2x. And so if we're going to figure out what that is, we'll need to use the chain rule. So h is g of u with u equal to f of 2x. So the derivative should be the derivative of g of u, which would be g prime of u, or g prime of f of 2x, times the derivative of u. And we could rewrite u as f of v, with v equal to 2x. So then the derivative of that should be f prime of 2x. And then times the derivative of v, which is 2. Everybody good with that setup for the derivative of h? It's the chain rule within the chain rule. The composition of a composition of functions. Any questions or no? Okay, so now we need to plug in 1.5. So we're now looking for the evaluation of this at x equals 1.5, which will be g prime of f of 3 times f prime of 3, all times 2. So far, so good? You guys are awfully quiet today. Everybody all right with that?
Yes.
Yeah, all right, just making sure. Okay. So then now we need to figure out what's f of 3. Well, f of 3 is given to us. F of 3 is 2. So this now becomes 2 times g prime of 2 times f prime of 3. And f prime of 3, we can use our calculator to evaluate. And g prime of 2, we can use our chart and get negative 3. So we have 2 times negative 3, which should be negative 6. F prime of 3. And so that will be 3 times the cosine of e cubed. And so that's negative 18 cosine e cubed, which what does that come out to be approximately?
Negative 5.915.
Negative 5.915. Does that sound good to everybody?
Yeah.
Yes.
Perfect. Any questions on part B? No? Okay, let's move on to part C. So for part C, we're now talking about inverse functions. And we're looking at g inverse at a point where x is 2, which what does that tell us about g? G should have a point where the y value is 2. And how do we figure out when g of x equals 2?
From the table.
From the table, exactly. So, oh, it's a negative 2, not 2, sorry. Should make sure I read the question right. So we're interested in does g of x equal negative 2? And looking at the chart, g of x equals negative 2 when x is 3. So we'll say that occurs at x equals 3. And if we're looking for g inverse prime at negative 2, that should be 1 over g prime of 3. And so what does that give us for our slope? It gives us the slope is equal to 1 over g prime of 3. And from the chart, that should be negative 4. And so the equation of our tangent line to the inverse of g at this point should be y minus 3 equals negative 1/4 times x minus negative 2, or x plus 2. Any questions there on part C? All right, part D is then asking us about this new implicitly defined equation, f of x squared plus g of x equals xy minus 1. So let's find dy dx for that at the point 3, 1. So we've got f of x squared plus g of x equals xy minus 1. If we want to take the derivative of f of x squared, that's a u squared with u equal to f of x. So the derivative of that should be 2u, or 2f of x, times the derivative of u, which will be f prime of x, plus the derivative of g, which is g prime of x. And then the derivative of xy, we use the product rule, x times the derivative of y, plus y times the derivative of x, which is just 1, and then the minus 1 becomes 0. So our dy dx value should equal 2f of x, f prime of x, plus g prime of x minus y all over x. Everybody good with that as the derivative? As our dy dx value?
Yeah.
All right. So then we need to evaluate this at the point 3, comma 1. 1 second, and we'll start doing that. You guys. Sorry about that. So if we're plugging in 3 for x, this should become 2 times f of 3 times f prime of 3 plus g prime of 3 minus 1 all over 3. And f of 3 was 2. And f prime of 3 we'll get from that equation right there. So we've got 2 times, I'm sorry, what was f of 3 was 2. Okay, so we got 2 times 2 times our f prime of 3 value, which is 3 cosine e cubed, plus g prime of 3, where g prime of 3 is -4 from our chart again, minus 1 all over 3. And when you evaluate all of that out, what do you end up with? Somebody must have gotten a value for that, right? Negative 0.352. Everybody agree with that? Is that what you guys all got?
Yeah.
Yeah.
Perfect. Any questions on that problem at all? All right, let's move on then and do another one that's a little bit different. This one is more about continuity and asymptotes and that kind of stuff. So take, we'll say 10 to 12 minutes, and then I'll check in with you. And we'll see how you're doing. If you need the full 15, we'll take the full 15. If not, we'll start reviewing it a little early. Sound good?
Mm-hmm.
All right, ready to go. So we're talking about continuity at a point, looking at if f is continuous at x equals -3. So there's 3 criteria for a function to be continuous at a point. 1 is that the function needs to exist at that point. 2, that the limit as x approaches that x value needs to exist. So that's 1 and that's 2. And then the third criteria is that 1 and 2 are equal. Everybody good with that being the definition of continuity at a point?
Yes.
All right, cool. So first off, does f of -3 exist? What's f of -3? Well, we should use this middle one because that's where it's equal to -3, and that's -3k plus a half. So no matter what constant k is, that value exists. That's an actual value, right? Then for the limit, to see if a limit as x approaches -3 exists, we need to take a look at the limit from the left and the limit from the right. So we need to see, does the limit as x approaches -3 from the left of f of x equal the limit as x approaches -3 from the right of f of x. And we should already know that the limit as x approaches -3 from the right is this one from the middle. It just is this. If we plug in -3 for x, -3k plus a half. So effectively, we're going to be seeing if the limit, or we're going to be finding the x values, sorry, not x values, but k values that make the limit as x approaches 3 from the left of f of x, which is the one for 2x squared plus 5x minus 3 over x squared plus 4x plus 3 equal to -3k plus 1/2. Everybody good with that or no? All right, so what's the limit as x approaches -3 of this rational function? Well, if you plug in -3, you end up with 0 over 0. So we can either factor and cancel, or we can use L'Hopital's rule, because this is 0 over 0, to take the derivative of both of them. So it doesn't really matter. Let's use L'Hopital's rule just for the practice here. So if we use L'Hopital's rule, which if this was the AP test, you'd write out that you were using it. The derivative of the numerator is 4x plus 5. And the derivative of the denominator is 2x plus 4. We still want that to equal -3k plus. Everybody so far so good?
Yeah.
All right, plug in our -3. -12 plus 5 is -7. And -6 plus 4 is -2. This is 7 halves. If we subtract a half, that's 3. And k equals -1. Everybody good with that? So that's the k value that makes all three of these criteria true. F of -3 exists. The limit as x approaches -3 exists, and those two things are the same. Good or no?
Wait, so the question says justify it. So on the AP test, is like showing our work justification enough, or do we have to like write a therefore statement or something?
No, all of your work should be enough justification. Just make sure that you're making the point that all three of those things are true, because that's how they want you to justify that a function is continuous at a point. That these three criteria are met. So make sure your work shows those three things. Does that make sense? Good?
Yeah.
Okay. Cool. All right, let's take a look at part B. We want to know what type of discontinuity f has at x equals 0. So as we are coming into 0 from the left-hand side, we're just looking at a function that is just a straight solid line. True? Right, kx plus a half if x is 0. As we come in from the left-hand side, it's just a half. Would you guys agree with that? In this middle piece right there? The limit as x approaches 0 from the left of f of x equals a half. True? Everybody okay with that? Nobody's saying anything, so it's a little unclear if you guys know what I'm talking about. All right. So, and then from the right-hand side, I believe we have 2 to the x over 3 to the x minus 1. Is that right? I think that's right. 2 to the x over 3 to the x minus 1. Yeah, so as we approach 0 from the right-hand side of that, what do we end up with? We end up with a 1 in the numerator. And then here, something very, very close to 1 minus 1. Or 1 over a number that's very, very small. And 1 over a very, very small number is an infinity. So if one side is approaching infinity or negative infinity of this discontinuity, then that tells us that we have a vertical asymptote there. And that tells us that it is an infinite discontinuity. Good or no?
What would be the other types of discontinuities then?
So there's 3 different types, right? An infinite discontinuity is when there's an asymptote. A removable discontinuity is when you've got something like this, where it just meets up there, but there's a hole. And then a jump discontinuity would be when it goes along and you end somewhere and then you pick up in some other place, but there's not an asymptote there. So there's a finite limit from the right and a finite limit from the left, but they're different. That's a jump. And then removable is that the limit exists from both sides and they're the same from both sides, but the function doesn't exist at that point. And then an infinite would be if from one side or from both sides it approaches infinity or negative infinity. Does that make sense?
Yeah.
All right, and then for the last part of that one, we want to find the horizontal asymptotes. So if we're looking for horizontal asymptotes, that means we need to look at 2 different limits. What 2 limits do we need to look at? The limit as x approaches what?
Infinity.
Infinity of f of
And
x,
infinity.
negative infinity, exactly. So first off, what do you guys want to do, infinity or negative infinity first?
Infinity.
Infinity, okay. So which piece are we going to use for infinity? The one where x is greater than 0, right? The 2 to the x over 3 to the x minus 1. So this becomes a limit as x approaches infinity of 2 to the x over 3 to the x minus 1. And as x goes towards infinity, the numerator there, 2 to the x, is very large, and the denominator, 3 to the x, is also very large, right? But this minus 1, that minus 1 will end up becoming insignificant. So we could say that this is the same as the limit as x approaches infinity of just 2 to the x over 3 to the x. And if they're both raised to the power of x, that'd be 2/3 to the x. And what happens if I take a fraction that's between 0 and 1 and raise it to a very large power? What happens to that? Should get very small and approaches 0, right? Think about 2/3 squared. Well, 2/3 squared is 4/9. 4/9 is less than 2/3, right? And then multiply it by 2/3 again, you get 8/27, that's even smaller. And 16/81, that's even smaller, and so on and so on and so on. And keeps getting smaller, it approaches 0. So we have a horizontal asymptote of y equals 0 to the right. And over here, as we approach negative infinity, we're going to use that rational function, which was what, 2x squared plus, was it 5x or something? I don't even know. 5x minus 3, yeah. And x squared plus 4x plus 3. Yeah. So if I plug in negative infinity, what do I get? I get infinity over infinity. Everybody agree with that?
Yeah.
Okay, so we have options. One option is to divide everything by x squared, but we have a new option now, which is we could use L'Hopital's rule, right? because infinity over infinity is an indeterminate form. So we could make this the limit as x approaches negative infinity of 4x plus 5 over 2x plus 4, which is still negative infinity over negative infinity. So we could again apply L'Hopital's rule and make this the limit as x approaches negative infinity of 4 over 2, which is just 2. So we'd have a horizontal asymptote of y equals 2 to the left. And you would need that justification of limits to show both of them. Everybody good with that or no? All right. We got a little bit of time left. I'm going to at least get you guys started on this one. And we will maybe have a chance to talk a little bit about it. This one was a calculator problem also. So I'll give you about 10 minutes and then I'll check in on you with this one. Sound good to everybody?
Yep.
All right, go for it. So to find the instantaneous rate of change at 5, or to estimate it, we look at the average rate of change on the interval surrounding 5, so the interval from 6 to 4, or 4 to 6. So g of 6 minus g of 4 over 6 minus 4, or 2 minus 5 over 2, negative 3/2. So is everybody good with part A?
Yes.
Wait, why don't you use the derivatives like in the formula instead of the outputs of g of x? Why don't you just use like that derivatives?
Because what we're looking at is an instantaneous rate of change, but it's a rate of change that we want to approximate. And rather than look at what it is at some exact values here, the better instantaneous rate of change is from the actual values of the function. Because I could have a function that does something like, it could have a super high slope right here. Let's say this is at 4, and then it could flatten way out, or even like have a complete turn and go back down. Let's say this is it. Let's say this is, let me draw my picture better. So let's say this is what it looks like at 4, and then it might flatten back out and then go way back up steep again or something like this. And let's say that this value right here is the value at 5. Actually, let's say this value right here is the value at 5. But if we were to, and then let's say this was where we finished it at 6. I know this is a very good picture, but your instantaneous rate of change here at 4 is super high, and at 6 it's like very, very negative. And so if we were to take the averages of those, we might end up with something that was like, 0, whereas the actual rate of change is much more accurate to this line between the two of them. Does that make sense?
Yeah, thanks.
Yeah. Sorry, the picture is not super great there, but yeah, the best way to approximate a derivative is by using the average rate of change if you don't actually have a function to look at. I think we'll just stop there actually, because we're already over time, and I am supposed to host a club in 9 minutes and all that. So we'll talk about B, C, and D tomorrow. We're going to do one more problem, probably 2 more problems tomorrow also, and then next week we'll move on with some more new material.